Our next example, lots of words here. The key is that we divided a bunch of things into four different treatment groups, um, and we're trying to see are any of the means different? Okay, and again, you see the data below that and our output from Excel given here. Notice in the slides I do not have it, but in your notes you see um, those QQ plots. We have not covered those um, in this course yet. We just kind of throw it in here. The QQ plots are those plots with those bands that you see on your notes right below the data. It is not a foolproof way to assess normality, but if you do see those plots, the idea is that if the points fall roughly along the diagonal line and stay within those curved bands, that you have approximate normality. We don't cover it in this course as an explicit topic simply because there are a lot of problems with using QQ plots. There's no real mathematical way to um, assess normality that's very good. They all kind of have blaring holes somewhere. Um, and so this is another one that we could use, but it's using your eyeballs to kind of make an assessment, which is never something we love to do as statisticians. And so it's really a very minor thing, but if you do see those QQ plots and you're asked to assess normality, if all the points fall roughly along that diagonal line and they stay inside those curved bands, we say that we're good on the normality spectrum. And so our null and alternative, notice this time we have four groups, not three. As always, our alternative is just at least one of the means is different. When we talk about our assumptions, again, nothing jumps out on the methodology. We have no reason to think the samples aren't independent. So again, this goes back to what we've talked about before. We're going to kind of assume everything is kosher unless we see something in the problem that says, wait a minute, I can't believe we would try to do that. So again, we're going to assume the samples are independent, the methodology is sound. We can only categorize these things into one group, not multiple groups. The data, as we said, are approximately normal. We looked at those QQ plots, again, printed in your notes, not on the slides. I couldn't put them on the slides here because they would be so small. The plot wouldn't make as much sense. And then we have to check our variances. So now we have to check our variances here. Each method has its own set of statistics. So our sample variance here, 5.5, close to 6.5, 17.8, and 5. And now this is where I would say there's a little bit of a difference there, in that these three are all within 2 units of each other, and then this one is over 10 units further away. So this is a little bit worrisome in that the variance is so high on this one group. So I'm going to comment on that. I'm going to say that's maybe a little bit of a problem. Okay, that third group has a much higher variance. Once you get past that, again, it's a lot of lather, rinse, repeat. Report the test statistic. Again, make sure you put the degrees of freedom. Those are given to you again in the output. Notice, in this case, you were not given a p-value. You could find one. Okay, so you could go on to Excel and find that p-value who you weren't given one. So if you weren't given one, you would just say, this is clearly one that I'm going to use the rejection region method, find that critical value from either the Excel output or the F table. Again, be able to use the F table. I cannot guarantee that you will always see one in the Excel output. Our test statistic would fall over here in the shaded rejection region, which means we would reject. And because we can reject, then we would conclude at least one of the means is different. And because at least one of the means is different, we then ask ourselves that follow-up question, well, which one or ones are different? And now this is the part where we're going to put the multiple comparisons into action, where we're going to say, okay, I need to test every single pair that we have. In order to not butcher the names of these things, as this is an industry I'm not extremely familiar with, if we just call them by numbers, we say we have to compare the first to the second, the first to the third, first to the fourth, second to the third, second to the fourth, the third to the fourth. That's 6 different tests that we have to run. Okay. We know that each one of them is going to be a t-test. How do I know that's going to be a t-test? Well, if I turn back a couple of pages to the notes to page 61, in the middle of the page where it says Bonferroni multiple comparison test, we've defined that and said the test statistic is a t with n minus k degrees of freedom, and then we have the formula. So if we go to our output here, we can determine the degrees of freedom for each one of these tests would be 16, and we can plug in the data to get a bunch of test statistics. So the first one would look like this. And so I'll give you the opportunity to think through this here yourself if you want, but make sure you understand where all of these numbers come from. These are our individual sample size. Notice in the formula, this was 1, 2, 1, 2. I'm replacing them with the letters that they abbreviate with. The mean squared error came from our Excel table, and the X bar came from our Excel outputs on the sample statistics for each sample. And so then you just plug in and get a value. Well, what do I do with a t-test statistic? Well, just as before, you have 2 options. You can then convert to a p-value and compare to alpha. Again, because we've made our adjustment here in the test statistic, we can compare that p-value to 0.05. Or we can just find a critical value and say, I'm going to compare this to the critical value. Notice that these are all 2-tailed tests. Remember, we talked about that, because if my alternative for the ANOVA is at least some of the means are different, then when I do the pairwise things, all I have is that same word different. Remember, different would be 2-tailed test, not a greater than, less than situation. And so I can find the critical value for 16 degrees of freedom for an alpha of 0.05 2-tailed test is 2.12. So if you want to hop over to your t-table, make sure you can confirm that you can find that critical value. 16 degrees of freedom, alpha of 0.05 for 2-tailed, the critical value would be 2.12 or negative 2.12 on that side. And so what that means is anytime this value is more extreme than 2.12 or negative 2.12, we would reject, because that means our test statistic would fall outside of that critical value in that rejection region. If it's in the middle, then that's a fail or reject, right? So the same logic we had before. So I know there's a lot happening and you might be a little bit overwhelmed right now, but it's the same stuff as we had before. I don't have a picture here, but if you want to draw your little bell curve right here, right, and then a line over here, 2.12 on the one side, negative 2.12 shade to the tails, and then draw where this value is right here, negative 0.7. And so because this value here would lie in the middle of that T curve you would draw and not outside of 2.12 and negative 2.12, that means we failed to reject. We cannot conclude these two are different, right? Fail to reject means we cannot conclude differences. Reject means we can conclude differences. Okay, go to the next one, do the same thing. Now we're going to compare these two together. Again, a lot of the numbers will be similar. The denominator will be similar every time. The difference is going to be what happens in the numerator, because the different X bars. In this case, we would end up with a value of 3. Notice this is going to fall in the rejection region. This is greater than 2.12. Again, if you need to draw a picture, you could. And so for this setup here, because this is in the rejection region, we reject the null, we can conclude that those are different. Okay, so this is the process that we're going to go through 6 times in this case, because we have 6 different things to test when we have 4 groups that we're interested in comparing. So same idea here for this pair right here, 2.93 would be that test statistic. Again, it's convenient. We have the same degrees of freedom in all these tests, and we have the same denominator in all these tests. That works because we have the same sample size for each of our groups. If you did have a scenario where one group had a different sample size, these numbers would be slightly different. Just take note of that. This would fall in the rejection region because it's larger than 2.12, so we would include the different. Notice what would happen if I'd flipped these, it wouldn't matter. If I'd flipped these and I'd put the CO group above the CO group, this would be here, this would be there, and all of a sudden it would be the same thing, except that'd be a negative 5.5 in the numerator, which would make this a negative 2.93. But again, we have a two-tailed test, so it's just we're rejecting if my test statistic is bigger than positive 2.12 or less than negative 2.12. Because my picture would be that I have those two critical values, and being on the extremes of either one leads me to rejection. So positive 2.93, negative 2.93 doesn't matter at all. Continue to work through the other groups. We can conclude these are different because we have a large test statistic. We can conclude those are different because we have a large test statistic. And then for my last pair, this is a very small test statistic, so we could not conclude those are different. Make sure you then also come back with a statement that outlines the overall picture, because what you've done is at this point we've only said, hey, something about this pair, something about this pair. We can talk about that pair, we can talk about this pair. So we just want to synthesize it and say, now let's talk about all the differences. There are scenarios where you would get reject 6 times, and you would say they are all different from each other. There are times when you would get only 1 or 2 rejections. You would say, hey, these 2 are different, but everything else is the same. Outline that for me. That's what we're going to do here. We're going to summarize with a statement. We can conclude there's a difference between the following pairs, and I listed out the pairs that I rejected that there was no difference, and I can conclude there is a difference because they had large test statistics.